Hey, so welcome back to our little workout here. We're getting ready to do an example problem. Our first example problem has an I-beam, right? I cross-section beam with some load on it. I think you're just probably sitting there wondering so your beam wants to hold a Honda and you work out to take by Fonda, but Fonda ain't gonna help you hold this Honda. My analysis don't want none unless you got beam fun. You can do side bends or sit-ups, but please don't forget them beams. That stress must be less than the yield or ultimate stress. I know that quick equation, saying my over I. Plug it in and calculate it. Tension or compression, gotta check it. So ladies, fellas, yeah? You wanna check some stress? Hell yeah! My over I. Easy as that.
All right. Well, I hope you're ready to get an example under your belt. Let's calculate the maximum stress occurring in this steel W18/71 beam if the applied bending moment is 250 kip-feet. Then we'll sketch the stress profile on the cross-section that's drawn at the bottom of this page. Now, the big equation that we need to remember for bending stress is that bending stress is equal to the sigma, the normal stress caused by bending. Sigma is equal to my over I. Hopefully that little song will help you remember it. If not, next class I'll try to give you another idea to remember this formula. All right, what do we need to know? Well, we need to know the moment. The moment is given to us here. The moment is 250 kip-feet. So that kind of settles that. What does this moment mean? I have the moment sketched there in orange as an orange arrow acting on the cross-section. And it's basically going from the bottom of the cross-section around the neutral axis to the top. All I'm trying to show in this picture is that we are basically bending this beam so that we create compression on the top face of the beam and we get tension on the bottom face of the beam. Okay, that's just what that moment means. So imagine I made a cut in my beam and this is the, moment, that positive moment force acting on the cross section. You can go back to last class where we talked about making cuts in our cross section and drawing in the internal forces. So I have the max tension shown on the bottom and the max compression on the top. So the distances to these points are what we need for our equation for y. I'm just going to call them y top and y bottom. In this particular problem, since the beam is symmetric about the neutral axis, y top and y bottom are the same. And so that means that sigma for the top, or sigma compression, is going to equal sigma tension. At least in magnitude. We usually put a negative for compression, positive for tension, but the magnitude of sigma in compression and sigma tension will be the same. All right, so let me summarize a few of these variables so far. We got m is 250 kip-feet. We figured out what y is graphically. Y top, or we can use y bottom, but now we need to get that in terms of like a real physical number. And so I'll scan to the bottom here to see the cross section, and again I'm going to draw in that y top dimension. Y top is going to be equal to, it looks like, half of 16.88 inches plus the thickness of that top plate. So it's going to be 16.88 inches over 2 plus the thickness of the top plate, or the top flange, which is 0.810 inches. Doing some math, that gives us the result of 9.25 inches. All right, so the only thing left to really solve this problem is I. I is the moment of inertia. Now, if we go back to statics class, hopefully you learned how to calculate moment of inertia and you guys are just like, super good at this. That's my always my dream. But just in case you don't remember, for rectangular elements, the moment of inertia about the center of a rectangle is 1/12 bh cubed. And then we're going to add in the d squared a term. We have to do this. This is the parallel axis theorem. And so we have to do this whenever those plates, those rectangles, don't match up to the overall center of gravity of our cross section. So the way I like to do moment of inertia is I like to divide my larger composite shape into smaller shapes. So here I'm going to take the middle, the web, that orange segment. I'm going to make that shape 1. And so I just kind of going to indicate it as shape 1. And shape 1 has a center of gravity as I indicated there on the segment. It's pretty easy to find the center of gravities for rectangular shapes. I hope you guys agree with that. All right, so now I need to get the contribution of shape 1 to my moment of inertia. So I have the 1/12 base times height cubed term. Now my base is going to be the thickness of this piece. The base is always parallel to the axis of interest. So I'm interested about the moment of inertia about the neutral axis. So I need to take the base that's parallel to that, which is 0.495 inches. That means the height of this plate is 16.88 inches. So I have 1/12 base times height cubed. Then I have to add my d squared a term. For my orange shape, because my center of gravity lies on the neutral axis, orange shape does not pick up any d squared. So d is 0 basically. So that's going to be 0 squared times a. And that is my contribution for shape 1. In addition, I have to add the contributions of the top and the bottom plates. So I'll call this top plate in red here shape 2. And let's go ahead and get the contribution of shape 2. So we add to this, we add another 1/12 base times height cubed. In this case, the base, parallel to the neutral axis, is the width of the plate, 7.64 inches. And then my height is going to be the thickness of that plate, 0.810 inches cubed. Plus, now distance is the distance from the neutral axis here to the center of gravity of shape 2. And so I have that labeled there in red. It's going to be that D2 value. So now I have to come up with what D2 is. This is just from geometry. So if I take a look at D2, D2 is just going to be, looks like half the height of the orange shape, 16.88 inches over 2, plus half the thickness of the red shape, 0.810 inches over 2. Sharpen your pencil and you'll get that D2 has to be 8.845 inches. All right, that's D in my d squared a term, and now I need to multiply by the area of the red. It looks like I didn't give myself enough room here, so I'm going to move this d squared a term to the next line here. So just repeating that d squared term. Get rid of that above. All right, now I need to multiply by the area of the section in red. The area of the section in red is just 7.64 inches times 0.810 inches. All right, all of this in red is now my contribution to the moment of inertia of shape 2. Now I have to take into account the contribution of the bottom plate, which I'll call shape 3. Now, if we look at shape 2 and shape 3, they both happen to be the same dimensions, and it's going to be the same distance away from the neutral axis. So really 3 is the same as 2 in this case. So I'm going to just kind of add here a 2 times this entire value in red for my moment of inertia. Now that gives me the contributions of shapes 1, 2, and 3 to the composite moment of inertia. So now my total moment of inertia, just go through the math there. you should get it's 1167.4 inches to the fourth. All right, it seems like I have my moment. I have y and I have I, so I'm all set to make my complete this first example on bending stress. You can see that I is in inches to the fourth and y is in inches. And so because of that, I might want to put my moment in inches. So I'm just going to convert 250 kip feet into kip times inches. So that's going to be 250 kip feet times 12 inches per foot. That'll give us 3,000 kip inches. All right, so I'll put that in on the top side of the equation, 3,000 kip inches times y, which is 9.25 inches. Divide that by 1167.4 inches to the fourth. If I keep track of my units, that's going to give me kips per inches squared, or unit of stress. And the value will be 23.77 kips per square inch, or KSI. There we go. We calculated the bending stress for this problem. All right, the very last part of the problem asks us to sketch the stress profile on this cross-section given. So the top is in compression and the bottom is in tension based on the direction of our moment. And so I'll just kind of plot those in. We know that the top and the bottom have the same magnitude. I'll just put the negative in there because our positive sign convention is for tension. So negative indicates compression when we're talking about forces, when we're talking about stresses. At the neutral axis, it has to be 0. This is a linear relationship. And then I go ahead and draw my arrows. So hopefully you followed along. If not, we'll have some practice again in example 2 and then next class. All right, see you at the next exercise.